Hello friends, welcome to e-learning platform of Dr. Bapuji Solanke Institute of Engineering and Technology's Mechanical Engineering Department. I am Sagar Gadkar and we are studying the subjects elements of machine design. We have already started with our third unit, that is design of shafts, keys and coupling, and we will continue the remaining part of this unit. So in this session we are going to discuss about the design of boost pin type flexible coupling. So it is similar to the flange coupling. In flange coupling we are generally using the bolt. So in this design procedure, instead of bolt we are designing a flexible pin by using the different mathematical equations. Okay, so this is the figure for design of flange coupling, that is protected type flange coupling. So in this figure, this D is nothing but diameter of the shaft. D, capital D, is outer diameter of the hub. D1 of the pitch circle diameter of the pins. So in previous design procedure, D1 is nothing but outer diameter. So here this D1 is nothing but pitch circle diameter of the pins. D2, outer diameter of the flange, is equal to 4D. So again remaining terms will be same like flange coupling. So this L is nothing but length of the hub, which is calculated by using the equation 1.5 times the diameter of the shaft. Width, that is B, is nothing but width of the key, is equal to D by 4. T is equal to thickness of the key, is equal to D by 6. L is equal to length of the key, is equal to L. TF is equal to thickness of flange, is equal to 0.5 times D. TP is nothing but thickness of protection, is equal to 0.25 times T. N is equal to number of pins. So here usually the number of pins are taken as 6. T is equal to torque transmitted by the shaft. Tau, permissible shear stress for the material, and sigma CR, permissible crushing stress for the material. So these are the notations used for the design of boost pin type flexible coupling. So we will see the actual design procedure for the boost pin type flexible coupling. So first step, design of shaft, which is same as we have designed in case of flexible coupling. So considering the shaft under twisting moment, so T is nothing but pi by 16 dq multiplied by tau. So from this equation, diameter of the shaft is determined. So this equation is derived by using the torsion equation, that is T by J tau by R. So equate this equation for T, you will get this value, T is equal to pi by 16 dq multiplied by tau. Okay, so it is the strength of equation of strength of solid circular shaft. So when the shaft is hollow circular, then the equation becomes T is equal to pi by 16 times D raised to 4 minus D raised to 4 multiplied by tau. So this is our second design procedure, that is design of hub, which is designed by using it as a hollow circular shaft, and by using this equation we can check the induced shear stress in the hub. Next is design of flange. So the flange is designed at the point where the hub and flange are in contact with each other. So that is the failure area where we have to design. So that failure area is calculated by using the equation tau is equal to force upon area. So from this equation, force will be tau multiplied by area. Okay, so this area is nothing but circumference multiplied by thickness of the flange. So what is the circumference of the circle? It is pi d. So d is nothing but capital D and thickness of the protection is tf. So this resisting area will become pi d multiplied by tf. Okay, and use this value in the basic equation of torque, that is torque is equal to force multiplied by radius. So the value of force is calculated here, that is force, that is pi d multiplied by tf multiplied by tau, and the radius is nothing but d by 2. Okay, so this is the equation, T is equal to pi d multiplied by tf multiplied by tau multiplied by d by 2. So from this equation, the induced shear stress in the flange is checked. Next is design of key. So key is designed as it is designed in case of the flexible or in case of flange coupling, protected type flange coupling. So first point is considering the shear failure of the key. So by using this equation, T is equal to L multiplied by B multiplied by tau multiplied by D by 2, the induced shear stress in the K is checked. And similarly, second step is considering the crushing failure of the key. So here the torque is calculated by using the equation T is equal to L multiplied by T by 2 multiplied by sigma CR multiplied by D by 2. By using this equation, we can calculate the induced crushing stress in the key. So this is the design procedure for the key. So in flange coupling we use bolt, so that the last procedure was design of bolts. Instead of bolt we are using a pin which is shown in the figure. So in this pin, this LB is nothing but, so this LB is nothing but length of the bush in the flange. This D1 is nothing but diameter of the pin. D2 is nothing but diameter of the rubber bush. Here the 5 mm clearance is provided for separating the flange in input shaft from the output shaft. So here we design the pin, flexible pin, by using the empirical relations. So our next step is design of the pin. So in that case, first point is diameter of the pin. So this D1 is calculated by using the equation D1 is equal to 0.5 times T upon under root of N plus 5 mm. This N is nothing but number of pins, which we have already usually taken as 6 number of pins. Second point is diameter of the rubber bush, that is D2. So for this pin, this black portion is nothing but brass bush, okay, which is of 2 mm thickness, and this outer portion is nothing but rubber bush, which is of 6 mm thickness. Okay. So here you have to calculate the outer diameter of the rubber bush, that is this D2, which is nothing but this D1. Okay, so this is D1 plus 2 multiplied by 2. So what is this 2 multiplied by 2? 2 mm brass bush from both the sides. So this 2 mm and this 2 mm, therefore it is 2 multiplied by 2 plus both sides rubber bush, that is 6 mm and 6 mm. So it is nothing but plus 2 multiplied by 6. So the D2 is calculated by using this equation. Next is third point, pitch circle diameter of the pins. So pitch circle diameter of the pins is calculated by using this equation, that is D1 is equal to 2 times diameter of the shaft plus diameter of the rubber bush plus 2 multiplied by 6, that is the 6 mm rubber bush thickness. Next is length of the bush in the flange, that is LB. Okay, so bearing load acting on each pin is calculated by using this equation. Okay, so how to calculate this equation? We know bearing pressure is nothing but PB, bearing load upon the area of the pin, that is L multiplied by diameter of the shaft. Okay, this equation we have already discussed in our first unit, that is fundamental of design. So in that case we have already discussed about the bearing pressure. So from this equation, bearing load is calculated by using P is equal to PB multiplied by L multiplied by diameter. Okay, so compare this equation here. So here this diameter is nothing but D2, length is nothing but LB, that is length of the bush in the flange, and PB is our bearing pressure. So this bearing load acting on each pin is calculated by P multiplied by P is equal to D2 multiplied by LB multiplied by PB. Next is torque transmitted by the coupling. So equation of torque is T is equal to force multiplied by radius. So here this force is nothing but bearing load acting on each pin, which we have already calculated here, that is P is equal to, force is nothing but P is equal to D2 multiplied by LB multiplied by PB. Okay, and R is nothing but diameter by 2. So here the diameter is D1, so radius become D1 by 2. Okay, so equation of torque becomes P multiplied by D1 by 2. So here this N is nothing but for number of pins, so T is equal to N multiplied by P multiplied by D1 by 2. So from this equation the length of the bush in the flange is determined. And last point is bending moment on the pin. So bending moment is calculated by using the equation moment is equal to force multiplied by distance. Okay, so by using this basic equation here, the equation of moment can be calculated as m is equal to p multiplied by lb by 2 plus 5 mm. Okay, so here this moment is calculated about this axis. Okay, so what is the force is p and distance is nothing but lb by 2, but the 5 mm clearance is provided, so the distance becomes lb by 2 plus 5 mm. Okay, so the equation of moment will be force multiplied by distance, that is p multiplied by lb by 2 plus 5 mm. Next step is bending stress in the pin. So bending stress is calculated by using our basic formula of bending moment equation, that is m by I is equal to sigma b by y. So from this equation, bending stress is calculated as m by I multiplied by y, and therefore this bending stress becomes m by z. We have this z is nothing but moment of inertia to the distance of extreme layer from the neutral axis. So the bending stress is calculated by using this equation, sigma b is equal to m by z, where this z is calculated for the circular section as pi by 32 d1 cube. Next is shear stress in the pin. So again, for stress the basic formula is tau is equal to force upon area. So this resisting area becomes pi by 4 d1 square. This is the equation of shear stress. Next is maximum principal stress. So the maximum principal stress is calculated by using the equation sigma 1 is equal to sigma x plus sigma y by 2 plus under root of sigma x minus sigma y by 2 bracket square plus tau xy bracket square. Okay, so this equation is for principal stresses, which we have already learned in our first unit. So it is the condition of biaxial stress system. So compare this equation with uniaxial stress system. So the equation becomes sigma 1 is equal to sigma by 2 plus under root of sigma by 2 bracket square plus tau square. So here this sigma is nothing but our bending stress, that is sigma b, and this tau is nothing but our maximum shear stress, that is the tau max. So the equation of maximum stress becomes sigma max is equal to sigma b by 2 plus under root of sigma b by 2 bracket square plus tau square, and the maximum shear stress is calculated by using this value. So this is the equation of maximum shear stress. So the tau max, compare this equation, comparing with this equation, therefore tau max is equal to under root of sigma b by 2 bracket square plus tau square. So this is the design procedure of boost pin type flexible flange coupling. If you have any doubt or query regarding this session, you can always contact me on this number. Thank you.